First of all, thank you very much for coming. I didn't expect so many people to come here to see this talk. Thank you. Thank you. So, there is a bit catch. So my wife is a hobbyist photographer, and recently she picked up film photography. Yes, the old school one with the film, with the development and all the grain and the analog stuff. So she also has a camera that can simulate image film. It's a digital camera, but it does film simulation, so it can apply grain, it make the color look like it's the old school film one, and that camera does it pretty well. And looking at that, I asked myself a question. Why did we stop doing that photography? Because look at this. This is the digital photo, and this one was taken on a film. These two photos were also taken on a film, and this is my picture actually. And those photos too. Look at the grain, look at the light leaks, look at the color. So it is something that is very aesthetically pleasing. And looking at that, I asked myself a question. Would it be possible to do something like that on Android? Yes, of course, you can do the post-processing of the image. You can apply filters, but I'm speaking about real time. So you can see the picture before you even take it. So I started exploring CameraX and found out that there is a thing that is called camera effect that actually gives you the opportunity to modify the image. There are two options at the moment. Image processor, which is a simplified version, which gives you the byte buffer with the image, so you can do the processing in your code, whatever you like. It's just the raw buffer. You can do Kotlin, Java, you can write C++ code, whatever you want. Unfortunately, there is a problem. It works only with the image capture use case. So no video, no preview, nothing like that. There is another option, which is called Surface Processor. And this one is low level. So it gives you the opportunity to do everything on your own, but the documentation suggests using Vulkan API or OpenGL, which means that you either write C++ code yourself or do the OpenGL setup on your own. And for my purpose of real-time image processing, we definitely want something very performant. Because just imagine, Pixel 7, even though it's not like the most modern phone, the output image is 12 megapixels. And if you want real-time performance, you need at least 30 frames per second. And just imagine, it would be roughly, well, not roughly, exactly, 360 million pixels per second processed. And that's at least, because nowadays we have even higher FPS, and 12 megapixels is not the highest resolution possible, so it's like the minimum requirement. So, and actually there is a thing that is very well designed to do such things, which is called GPU. So, why is GPU? So basically, the difference between GPU and CPU is this. So GPU core compared to CPU one is very, very simple. It doesn't have branch prediction. It doesn't have out-of-order execution. It has very small cache. And all those fancy things we like in CPUs that make them fast are actually sacrificed to save the space. And that saved space is occupied by many more cores. So you can do a lot of parallel processing at the same second. Additionally, GPU relies on a concept called SIMD, single instruction multiple data, which is a concept when the processor does this exactly the same operation over several chunks of data at the same time. So GPU has only a single stream of commands, and those commands are executed on all the cores at the same time, which is actually good because you have millions of pixels and you do the same operation over them. On the contrary, CPU, sorry, did I say CPU previously? It was about GPU. On the contrary, CPU is MIMT, which is called multiple instructions, multiple data, and CPU cores load the code and execute instructions independently from one another. Of course, it doesn't mean that CPU cannot do SIMD. There are SIMD extensions, and modern processors use them a lot. It's just not the scale of GPU. So this is basically how the execution looks like. So the CPU core does the tasks sequentially, while GPU can do it simultaneously. Basically, GPU is a high through output processor, and CPU is low latency processor. So they're basically designed for different tasks. So, and if we go back to the camera effect APIs, we see that to make that work, you need to build a use case group. So this is the example of the basic setup of camera provider. So, but instead of using the default use case, you need to add use case group builder and apply effect after the use cases you are going to use. And the camera effect is basically a very simple interface that does the only thing. The key purpose of the camera effect is to return a surface processor, which does all the transformations and all the processing you need to do. And the surface processor is actually the interesting thing that is needed to be implemented properly. So there are basically two callbacks, on input surface and on output surface. On input surface, the library requests a surface where it will write the original frames, and your implementation will consume those frames to do the transformations. On output surface, we need to consume the surface that library provides us. Basically, we are getting the surface. So we are providing a surface where the library writes. Then we read the surface, do the processing, and write the output to the surface provided on output surface. And then library does all the things with displaying, saving the images, whatever you want. So I'm not going to show all the implementation of surface processor because combined with the renderer, it's pretty complex, but it is open source. There is a default implementation in the CameraX library. Unfortunately, it is not public. It's internal to the library, so you can't use it, but it is open source. So you can find it on the GitHub. In the end, I will give you QR code with all the links, so don't worry about that. So instead, I'm going to focus more on the shaders because in the library, the shaders are really basic, but that's actually the thing we would like to explore more. So what a shader is? A shader is a special program that is executed directly on GPU and done it in parallel. So shader is user-defined and written in a special C-like language called GL shader language, or short GLSL. So this is the OpenGL rendering pipeline, and here 2 points. There are 2 steps where you can write your own shaders. So vertex shaders and fragment shaders. And basically, there are 2 types of those shaders in the rendering pipeline. So vertex shader is a shader for transforming the objects. So its key purpose to transform the the local model coordinates to the screen space coordinates. So basically, the object is correctly placed in the screen. However, since we have a camera surface, it's just a two-dimensional object, you do not need to do any complex transformations. The only purpose is just to fit it properly in the output view. And it's really, really basic. So usually you're not going to do anything else with it. So this is how vertex shader, default vertex shader looks like. There is, however, one important thing. So UTEX matrix is a matrix that is provided by the AndroidX library. And it can contain some device-specific bugs for maybe optics, or maybe there are some hardware bugs or things like that. And it is going to fix that. So it is required to use that matrix the way it is used in the library. And the more important thing is a fragment shader. So fragment shader is a thing that processes the fragments. So fragments is a result of rasterization, but again, our images are already rasterized. So we just have a set of pixels, and what fragment shader does is basically takes the input pixel and provides the output pixel processed in some way. So this is how the basic fragment shader looks like, and let's dive deeper what happens here. So the first lines are directives. The line 1 says that we want to use version 3.2 of GLES. And the line 2 is that we want to use extension called image external ESSL3. It's basically an extension that makes camera images look like regular images for the language. So you can use basically camera images exactly as normal images that are loaded. It also introduces type called sampler external. You can see it on the line 4, and well, it's basically the compatibility type, which you can ask to provide you a pixel. Then we have inputs and outputs defined. So line 6 is texture coordinate. Basically, it is XY coordinates of the pixel in float format from 0 to 1. They are coming from previous vertex shader. And output fragment color. Basically, there is a requirement from fragment shader to provide an output color. So there are maybe more outputs, but if there is only one output, it is treated as a color because it is default one. And then goes the main program, which is executed for every pixel. This is the basic shader that just relays the input pixel to output. So we are writing what texture provides us to the output color. Sorry. Sorry about that. So it just writes the output pixel to the output. So yeah, and let's speak a bit more about GL shader language. So GL shader language is designed for graphics and geometry processing. So there are several scalar types, Boolean, integer, uint, float, and double, which you're familiar with. So, however, there is one point that the default precision for that is not defined in the shader. There is no specification for OpenGL for embedded systems. And basically the precision is what the value range for that type. So it can be 2 bytes, it can be 3 bytes, it can be 4 bytes, and it's not specified by default. Usually you want at least medium or high precision, which needs to be specified explicitly. So the type system is shown, like in Kotlin. You cannot do some things and expect compiler to understand what types you want. So you can't assign integer variable to float. You can't do mathematical operations over different types. The types have to be exactly the same. There are very convenient types for vectors and matrices. So they can be of 2 components, 3 components, and 4 components, not more, but that's usually enough, because if you have color, it has usually 4 components, alpha and RGB, or if you have 3D coordinates, it's just usually 3 values, and that's usually enough. So for the majority of cases, it is enough. So the same with matrices. However, there is one difference. So matrices can be only floating point, but for vectors, you can have integer vectors, you can have float vectors, you can have unsigned integer vectors, and yeah, things like that. There is a very convenient thing which is called swizzling. It works only for vectors, which allows you to construct new vectors from other vectors. For instance, if you have vector of 4 components, you can just write .rgb, and it will create a new vector with RGB components. The same works with XYZ, so it's just convenient. Additionally, there are operations component-wise. So if you add or multiply vectors, it will automatically just do component-wise operations. So you can see, if we multiply vector by vector, it would be exactly the same as destruct the vector and do the component-wise operations manually. And there is one more type, which are called opaque types. Opaque types are not the values itself, but rather references to the external objects, for instance, an image. So you do not hold the whole image, you just read from image by reference. Okay, so you good? Are you still here? It was pretty intense, I think. So I'll give you a small break and show what you could do with fragment shaders. So this would be the basic shader for grayscale. So function main just reads from the texture and applies grayscale transformation to the pixel and writes the output, of course. So this is the original image and the image taken with the filter. It's easy to do sepia. It's exactly the same as grayscale, but you can also do the you just apply additional tint, and it starts to look like this. There is one interesting point that in GPU, there is no random at all. So you can't generate random images, random values. So the community came up with some commonly used functions for generating some sort of random. So for instance, if you can see the function simple noise, which does the based on trigonometric functions and create like sort of random values. They're not really random because they're completely predictable, but it looks like random enough. So we can apply some sort of a noise to a grayscale image. I'm not sure if you can see it here, but the comparison, so the right image, you see that there is some small noise on that. Additionally, yes, it's easy to implement literally any transformations you have in Photoshop or other image editors, for instance, brightness and contrast. And it will look like this. There is, but when I discovered that, I also saw that there are other types of shaders. And those shaders are called compute shaders. They are not the part of rendering pipeline, but they allow you to do any computations you want. So Compute Shader is supported starting from Android 5 and heavily relies on special things called shader storage buffer objects. Basically, it's a thing that allows you to map some chunk of memory to the shader and so it can access. Additionally, it allows you to have arrays with unspecified size. So compute shaders work in a thing called workgroup. So a workgroup is a group of threads that are executed in parallel and do some work together on a task. The threads are in quotes because it is not a real thread like operating system thread, but it is similar in a way that the computations are done in parallel. So local space is completely static. You define it in shader. It is defined in 3D space, so you have how many X, Y, and Z components, and they are multiplied, so they shape a 3D space. So also the purpose of existing of a work group is that they can share data within the group efficiently. So there are some special functions, memory barriers, that ensure that all the calls, all the reads and writes to the buffers are done before this memory barrier executes. So from the Kotlin code, when you launch shader, it is called dispatch. And in that dispatch, you can specify how many groups you want to launch. And this is dynamic, which gives you a space for flexibility. So a total number of shader invocations will be local space multiplied by how many groups you are launching. Ironically, even though I'm showing general purpose computing, I will show how to apply some filters to the images. But instead, I will treat it not as image, but just an array of bytes. So for instance, an image of 1024 by 1024, you can divide in many ways. It can be a group of 16 by 16 tiles defined in the local space and 64 by 64 groups, or you can just do a very small group of 1 pixel and launch it as many times as you have pixels. And well, basically in any way that adds up to 1024 by 1024. So you see the line 3 is the local space definition. It is completely static. So if you define it in shader, then you can change it. That's why you have dispatch instruction, how many work groups you want to dispatch. So lines 5 and 9 define the buffers. So in line 5, we define the read-only buffer, which we load with the data we want to process, basically input data, and write the data to output buffer. Additionally, we define 2 uniform variables, width and height of the image, because since we have only one-dimensional array, we just want to know how this image is, basically what are the dimensions of the image. So uniform is a special modifier that basically means that this variable doesn't change between shader invocations within one draw call. And this is the code of the shader. So function main is pretty basic. So we just look for global invocation ID. So the shader has a number of variables that allows it to read what is the global invocation ID, what is the local invocation ID, how many groups there are, and well, basically things that help organizing the work. So we check that it is within the bounds, transform the pixel, yes. So image, usually BMP images are in ARGB format, so we need to unpack the integer into the color components, perform the operation, and pack it back so the caller can read in the same format it has feed the data. And this is the Kotlin part. So to set it up, we need to create the byte buffer and map it to the shader. So we just instruct OpenGL that this variable in shader is connected with this buffer. So you see here in layout bindings that we specify layout bindings and locations, there are basically IDs of the objects where we want to bind it. Now see here, the line 17, it has input binding index. This is the index specified in shader. We just know where to bind. There is another option we can ask after the shader is compiled. We can just ask for location of that variable, but it's just faster. Similarly, we do the binding for output buffers and dispatch. So yes, we set the image width and image height. Run the dispatch, you see, so here we specify what is the width and height of the image because our shader operates over pixel and the workgroup is 1 pixel. We launch it as many times as there are pixels. And we put after that the memory barrier to be sure that all the buffer writes will be completed by the time we want to access this buffer. And after that, consuming the result. Basically, it is simple. Again, binding the buffer, reading the data from it, and copying the data to the bitmap to create a new one. And unmap buffers after that because you do not need them after. So here I have a small demo. It's not a benchmark by any means, but how it looks like to run this shader processing compared to pure Kotlin counterpart. So basically, I've recreated the same effect with Kotlin. It's just grayscale, nothing complex, but it runs only in one thread. Sorry, I was too lazy to parallelize it, but it's pretty good demonstration. So the shader is almost instant. Kotlin will take roughly 12 seconds. Of course, you can make it parallel, but if it is run on device, so you can have how many cores they usually have? 8. So maybe it will be 8 times faster, but usually not. And so you see the shader was run. So all the computation was run in 250 milliseconds roughly, but it is everything with the OpenGL setup. Just dispatch works roughly 200 microseconds or something like that. So OpenGL setup is actually takes much more time than actually the execution. So in conclusion, I'd like to mention that OpenGL is not really easy, but it is very, very rewarding. So because it is possible to offload very heavy computations to the GPU, because mobile phones are usually not treated as something you want to run computations, but maybe they should be. Maybe we can do something like that. So GLSL is really decent for graphics. Yes, there is one thing I haven't mentioned before. Shaders are compiled right on the device, which gives you a lot of flexibility. Basically, shader is just a string of text. So, and OpenGL has built-in compiler that compiles the shader. So basically, you can just push updates from backend, and your application can have variability of shaders without any updates. I'm not sure what Google Play stands on that topic because Google Play doesn't allow code side loading, but so do not risk it, but technically it is possible. And it's a great field for creativity. Oh yes, by the way, shaders work for video with CameraX work exactly the same way as for images. And there is a small video I've recorded yesterday, and yeah, just recorded this video was in 4K 30 frames per second, and I've created some glitches, kind of cyberpunkish. Yeah, and that works instantly. So creating that shader took me, I don't know, half an hour maybe. So that's not something complex. Yeah, and yeah, I've left for you my bento, so there is a section with droidcon links. Feel free to, yes, feel free to copy it, feel free to see it. Yes, if you want to chat, I'm open to chat, so any questions, you're welcome.